Good morning, guys. Today we're going to be looking at Einstein's time dilation and Lorentz's length contraction. In 1962, David H. Frisch and James H. Smith from MIT and the University of Illinois did an experiment to show us that Einstein's time dilation worked. They explain early in the video, what we know, that when objects are traveling at ordinary speeds, that the time dilation does occur, but it's so small that it's negligible. That it really takes clocks moving near the speed of light where we can really see a difference. So in 1962, Frisch and Smith went up to Mount Washington, and they used technology like a simulator, an oscilloscope, and a photomultiplier. And what they were able to do is, and they also, you can kind of see behind here that they had a bunch of iron bricks right here. And what they did is they put the simulator underneath the bricks and they closed it off to the light. And what they were able to do is they were able to stop Mu Mesons inside the simulator and then wait for them to blow up because they have a very short half-life. And by collecting all this data and realizing that these Mu Mesons are traveling at about 0.96 the speed of light, they were able to predict about how many mesons would still exist at sea level. But remember that this was relative to the mesons that were stopped in the simulator, and that were at rest. So once they got a calculation that there were very few actually of these mesons that were going to survive over an hour at sea level, they packed up all their equipment, went down there. They didn't need as much iron because of the atmosphere, which makes up a percentage of it. And they were able to set up the experiment at MIT, which is a bit of a distance away from Mount Washington, but at sea level. And then when they did the experiment again, this time around, they determined that there were a lot of mesons that had survived, a lot more than they predicted. And this showed that when objects are traveling near the speed of light, that the time is different from, and they do follow this Einstein time dilation. Frisch concluded his discussion by talking about Lorentz's length contraction. I really enjoyed this and how he states it, that if you could catch a ride on a hot meson, then you can make a mountain out of a molehill. And what he means by this is that if you rode on a rocking chair on a bunch of mesons, you would seem to be at rest. You would then see Mount Washington approaching you at 0.96 the speed of light, and then sometime later sea level. If you were to calculate the height of the Mount Washington, it would correspond to a hill, not a mountain. So therefore, Mount Washington is really a hill compared to what it really is. And that's how it would be seen from the perspective of the mesons. We have a couple of pictures here of these guys performing the experiment. There's the first one here, and then there's the second one with the simulator. And then here's some data of what they were tracking as the mesons were decaying inside their simulator on top of Mount Washington in New Hampshire. Now, as far as the Lorenz contraction goes, we can take a look at it in terms of the Galilean transformation and taking into account, Einstein's time dilation. So if we had two events here where we had a frame S, which was at rest, and S prime, which was moving, we would realize here that if an event occurred, that we would get x is equal to vt plus x prime times that time dilation of Einstein there, because the second one is moving. And solving for x prime, we would have x prime is equal to this here, x minus vt over 1 minus v squared over c squared. Now, if we consider v small, we have the familiar equation, which is the displacement is equal to the velocity times the time. Now, if we consider next taking into account the time in this reference frame, and we consider that we have we look from the reference frame that's moving, S prime, and we put 2 clocks in both reference times, then we realize that the clock in S would have a lag time. And this would give us T prime is equal to 1 minus V squared over C squared times T minus the lag time of the first reference frame. And this time here, completes the Lorenz transformations. So we get the first one, instead of like Galileo where we have x prime is equal to x, we've got x prime is going to be equal to gamma times x minus vt, where gamma is 1 minus v squared over c squared, and we get y prime is equal to y, z prime is equal to z, and t prime is different. So in Galilean, it's t prime is equal to t, but we can see here through the second example here, considering the lag time of the first thing, and that both clocks are moving slow here relative to each other, that we've got gamma t minus the lag time. T prime is equal to gamma t minus the lag time. So as far as the derivation goes, there's not a lot of time in this video for that. So I leave that to a future time. So here are some good resources. We have Halliwell's book, Special Relativity, and then Frisch's experiments online at YouTube with the Mu Mesons, and it's really worth watching. Well, that's it, guys. Thank you so much now. Bye.